It's my pleasure to present Professor Stefano Serra Capizzano from Italy, Insubria University, and also Uppsala University, Sweden. And he will speak about the GLT theory. So please, Stefano, go ahead.
Thank you very much. I think that you hear me, no? Yes.
Yes, yes.
Yes, so thank you for the invitation. Thanks to Alexey, to Vladislav, and to Tatiana, of course, for everything. And I'm very happy of this, of having this opportunity, because I have to be sincere and frank. I really like Russian culture, Russian science. And in fact, when I was young, one of a person who I consider one of my mentors was Eugene Tertishnikov. And somehow the talk could be also related to what it was his activity in the 90s. In fact, he extended the Zigo-like results for sequences of Teplitz matrices generated by Lebesgue integrable functions. So extending the result of Zigo and of Teplitz itself, of Becher, Silberman, and so on. So it was a big achievement, in my opinion, also because the technique was completely new. Instead of using orthogonal polynomials or analytic tools, used tools that today I would call asymptotic linear algebra. And since the problem was of asymptotic linear algebra, I think that it was the tools used by Tertishnikov were the most appropriate. So what is GLT? The T is in common with the activity of Tertishnikov, because GLT is the acronym of generalized locally Teplitz. Instead of starting with the formal presentation, I will pass the main message of this GLT. So if you consider this class of matrix sequences, the interesting facts are two. First of all is a star algebra. So if you make algebraic operation with matrix sequences in the GLT algebra, you stay in the GLT algebra. Every sequence has a symbol, and this is very important, which describes asymptotically the behavior of the singular values. So the more the matrix is large, somehow the more precise is this description. And under mild conditions, also the eigenvalues are described asymptotically. Then if you make algebraic operation on the sequences, on these sequences, the resulting matrix sequences will have a symbol which is obtained by using the same algebraic operation. So you have a way for building very complicated matrix sequences very far, for instance, from the Teplitz one, and still have a description which is quite accurate of the eigenvalues and singular values when the matrix size tends to infinity. So this is the mathematical result, which is the most interesting. The other aspect, which is also very interesting, is that virtually when you have a partial differential equation and you make a discretization, by using virtually any kind of local approximation scheme, no matter if you are using finite differences, finite elements, isogeometric analysis, finite volume, discontinuous Galerkin, whatever, then you end up with a matrix sequence that belongs to this algebra. So somehow the power of this theory is that is able to give a unified treatment to the asymptotic behavior of singular values and eigenvalues of a very large class of magic sequences appearing in application. So somehow I anticipated. Sorry? Okay. So somehow I anticipated what was the main message. So now let's start. So the framework is the following. You have a linear partial differential equation, or a linear fractional differential equation, or integral differential equation. You make use of some numerical method, linear numerical method. You end up with a large linear system, ln un equal to gn. And the framework that I like to consider is not the single matrix Ln, but the whole matrix sequence. So as the fineness parameter tends to 0, the matrix size tends to infinity, the dimension of Ln, and the message is that Ln is an asymptotical spectral distribution described by a spectral symbol or singular value symbol, and the GRT sequences represent a tool for computing somehow in an easy way this kind of symbol. Then if you put GRT together with the Korotkine theory, by the way, another Soviet Russian mathematician, you have also tools for designing fast numerical methods. So the message is that in this case, Ln is usually a GRT matrix sequence, and there is also this linear positive operator character if you use some Galerkin approximation. When I say usually, is because the theory is very general. So if your domain, so which are the assumptions on the domain? The domain should be just Peano-Jordan measurable. So its characteristic function should be Riemann integrable. The variable coefficient of your partial differential equation should be just Riemann integrable. So this is much weaker than encountered usually in real application. What is the constraint is on the grid. The grid can be not uniform, but should be described by a function somehow applied to a uniform grid. So the right framework is that where the gridding is obtained using graded meshes. So these are the books on the GRT theory, and then after 2 books we were exhausted, so we passed to longer review papers, more than 100 pages, because we had no energy for writing other books. But why all these results? Somehow there is room for generalization, of course, and it looks like an academic mathematical passion for generality. But somehow the real truth is almost the opposite. It was due to application that we were somehow invited to extend the theory. In this sense, it is interesting the sentence that Shakespeare gives to Hamlet. There are more things in heaven and land than in your philosophy. And if one wants to rephrase in a mathematical setting, the message is the following. No matter how general is your theory, there will be applications which are described by this theory. And more important, there will be more applications which are not described by the theory. So the theory is not general enough to contain everything. Like the message is the nature has more imagination than us. So this is the setting. So you start with MM of C, complex matrices of size M, and this is the space where your symbol, GRT symbol, will belong. You consider a sequence, a metric sequence an of size dn strictly less than dn plus 1, so that when n goes to infinity, you have the dn goes to infinity. So like it happens when you consider finite section of triplets operators, or when you consider an approximation of some infinite dimensional operator, like the one in a partial differential equation or a fractional differential equation, if you like. Psi is just measurable on some set D in Rg with G larger than 1, and psi, the symbol, is ms valued with some s larger than 1. We have to restrict, otherwise mathematically we will see it has no sense, the measure of the domain to be positive unless to infinity. Mu can be the Lebesgue measure, and we write that an is distributed in the eigenvalue sense like psi on D. Now I give just the informal meaning. If the size of your symbol is just 1 and psi is continuous, then it means that a suitable ordering of the eigenvalues in correspondence with an explicit grid on D is able to reconstruct the surface asymptotically as n tends to infinity t psi of t. When s is larger than 1, and this is important, and again psi is continuous, then the eigenvalues of your metric sequence an split in s sets of the same cardinality in S set, and each of this set reconstruct asymptotically the surface T lambda j of psi of T. Since psi is matrix valued, it will have S eigenvalues, and then these eigenvalues are functions, and the eigenvalues of your matrix sequence will distribute like these S different functions. Of course, there is the same notion for singular values, and everything is completely natural. In that case, instead of considering the eigenvalues of psi of t, you will consider as function the singular values of psi of t. So this is the formal definition. You consider any capital F continuous with bounded support, and you consider this average. 1 on dn, dn is the size of your matrix, the sum of capital L on lambda j of an, and you say that an is distributed in the eigenvalue sense as psi on D if this limit converge to this special function. Of course, the trace does not show up when S is equal to 1. And of course, there is the same notion with the singular values by replacing lambda j of an by sigma j of an, so using the singular values, and by replacing, instead of psi, you have to use the modulus of psi, where the modulus is psi star psi to the power 1/2. So instead of the eigenvalues of psi, the singular values of psi will describe asymptotically the singular value of the whole matrix sequence. And here, for showing that nature has more imagination than us, if you consider the discretization of a Laplacian in D dimension, in a square in D dimension, then you discover that using finite elements of degree of regularity 0 and degree of each polynomial p, your S, the size of your symbol, is p to the power d. And this is kind of striking if you think about. If you think to have a polynomial of degree 5 and you are in a 3-dimensional square, you will obtain 5 to the power 3, that is 125. It means that the eigenvalues of your Laplacian will be described by 125 independent functions, which are the eigenvalues of your symbol. But if you impose more regularity, for instance, you impose that the regularity is ck, then the size would be p minus k to the power d And if k is maximal, that is p minus 1. So instead of considering the standard finite elements, you consider isogeometric analysis, the S is equal 1. The isogeometric analysis was the one proposed by Tom Hughes several decades ago, and it is very good for engineering purposes. But the nice thing from a spectral point of view, and this is obtained using this GFT approach, is that it is the only kind of, in this family of approximation of the PD that gives rise to S equal 1. So there will be just one function describing the eigenvalues instead of P to the power D type like in the finite elements. By the way, this explains why, from a numerical linear algebra point of view, isogeometric analysis can have a somehow easier treatment, while finite elements with high order can lead to some difficulty. Then somehow we want to go beyond. If you consider systems of partial differential equation, so instead of having one partial differential equation, you have a system of coupled partial differential equation with different partial differential equation. Then instead of having a GLT structure, you will have this kind of block structure in which every AJK is still of GLT nature. And now the question is to understand how to describe spectrally the eigenvalues and singular values asymptotically of such kind of very complicated structure. And it turns out that if the partial size Ni divided by the global size tends to some Ci, so there is some kind of regularity, of course C1 plus C2 plus C nu equal to 1, then we are able again to describe the symbol. But in this case, the dimensionality can be very high. So S could be some G times P to the minus K to the power D, where the P minus K to the power D was the one as before. A G is a complicated function depending on the number of partial differential equations and on this ratio values C1, C0. This is an example that we worked out practically. It concerns organoid. So it is something very interesting because if a patient has a cancer, instead of trying the treatment on the patient, we take few cells of his skin, for instance, we make grow in a laboratory until we have N cells, and we make the treatment on that organoid, that artificial part of the body, and we see what works better. When we find the one that works, then we go to the patient. So here you see that the number of cells is the number of partial differential equations. So very easily you go to several millions of unknowns, but we were able with the theory that I just scheduled before to give a description of the asymptotic spectrum, of the asymptotic singular values, and then construct on this basis fast methods of precondition and conjugate, of precondition and creep of type or of multi-grid type. So I didn't stress enough, but at the end, one of the aim is to use the spectral information for finding fast methods. I insist on the theoretical part because somehow I like more theory than applications, even if, as I said, applications are very important also to challenge theory. So let's go to some tools. We need some kind of approximation theory for matrix sequence if we want to treat difficult matrix sequences. So given AN, the matrix sequence of your problem, we write that B and M, so we introduce a new parameter M, is an approximating class of sequences if AN can be written as the simpler object B and M plus an error term. Usually, when you consider your Weierstrass theorem, for instance, on the interval 0, 1, the approximation, the error term is given just by a quantity. Here you have to split, because in numerical linear algebra, this is known. Something is small if it is small in rank, or it is small in norm. Because if it is small in rank, then, for instance, if you want to invert using some Sherman-Morrison-Woodbury formula, you can obtain easily the inverse. So the error is to be split in two components, R and M, which takes care of the rank part, N and M, which takes care of the norm part. So the rank should be relatively small with respect to the dimension, so less than dn, which is the matrix size, times Cm, and the norm should be small. And the small is given on the condition limit as m tends to infinity of omega m and Cm equal to 0. This is an approximating class of sequence, which means that your magic sequence, difficult magic sequence, is AN, and you approximate by a class depending on M of easier magic sequences like B and M. So in our case of discretization of variable coefficient differential equations, we will use locally constant coefficient differential equation. So we will use locally, so in part of the domain, Toeplitz structure. And this is also justified the name locally Toeplitz, and then the generalization generalized the locally Toeplitz. So if this is a good definition, there should be also some good theorem, and this is the main theorem. There are many, but this is really the most important for the approximation. So you have your AN, which is your difficult magic sequences. B and M is your approximating class of sequences, and now it's called ACS for AN. Then, for some reason, mysterious, because you have chosen BNM to approximate in a simple way, you are able to compute the spectral symbol of BNM for any M. And so you know that BNM is distributed in the singular value sense as psi M. And you are, once you have psi M, you make a convergence in measure and you obtain psi. If these three assumptions are satisfied, then you can close the graph, and AN is distributed in the singular value sense as psi. So this is the main theorem for deducing the singular value distribution of matrix sequences from simpler matrix sequences. So a kind of approximation theory which is tailored for matrix sequences. And of course, as you see in the right, if everything is Hermitian or quasi-Hermitian, so small perturbation of Hermitian object, then you can infer the same kind of result in the sense of the eigenvalues. There are now generalizations which are very recent, due especially to Adriani and Schiavone, the generalized ACS, approximating class of sequences, which are used when the dimensions do not match exactly. So the difference of the size between B and M and A of N is a small O of the dimension. This reminds another thing related to my Russian mentor, Tertishnikov, what he was used to call the extra-dimensional approach. So this is an evolution of his idea, and this idea was never published by Tertishnikov. So when we published the result, we acknowledged that the talk with him 20 years ago somehow remained in our mind, and then it evolved in these new notions. So let's go to the GLT. As I told you, the GLT is a star algebra of magic sequences. So I first describe the generators. So you take some function f, which is Lebesgue integrable on this domain minus pi pi to the power d, and having values in the square matrices of size s. You can consider the Fourier coefficient fj, and when the dimension, the d is equal to 1, you have a standard Toeplitz with the fj, which are blocks of size S. When the D is larger than 1, you have D-level structure. And of course, they are difficult to describe, but it's not difficult for us. It's just the discretization of some Laplacian in more dimension gives you the idea. So a D-level matrix is a Teplitz matrix in which each block is a D-1 level Teplitz matrix, and so on, until you arrive to D equal to 1. Then there is this important result, which was found independently by Tertishnikov and Zamarashkin in 97, 98, and by Tilly in 98, that the Teplitz sequence generated by N is by F is distributed in the singular value sense FF, and if the symbol is Hermitian valued almost everywhere, then the same thing holds for the eigenvalues. The techniques used by Tilly and Tertishnikov and Zamarashkin are interesting enough, both of asymptotic linear algebra nature, but they are not the same. So it was really an independent contribution as technique, even if the result was in fact essentially the same. Then other component. The other component is even easier. Diagonal sampling matrices. This is important for acknowledging the variation along the diagonal of your matrix, which should be smooth somehow, so described by a function. And this happens when you discretize, for instance, a partial differential equation with the non-constant coefficient. You will have evaluation of the function or a local integral, which then is almost the same. Then the eigenvalues of DNA are clearly the sampling of this A of X. So in this case, the DNA is distributed, both eigenvalue and singular value sense, as A of X, and the assumption on A of X is that it is Riemann integrable in the interval 0, 1. So remember that for the A, the assumption is Riemann integrable because we make sampling, while for the Teplitz part, the assumption is L1 because we consider the Fourier coefficient. So these are the two main components of the GLT algebra. They are all magic sequences of the same size. And then we go to the third component, which are the zero distributed matrix sequences. And by the way, the zero distributed matrix sequences are those such that the singular value have as a symbol 0. So there is a cluster to 0. These matrix sequences were called by Becher little nothings because they are nothing, but they are kind of important. Because if you consider a Laplacian and you change the boundary condition, then the difference between the two matrix sequences is zero distributed. If you take an integral equation, since there is the integration, so the operator is compact, you will discover that the matrix sequence that arise in the discretization is distributed like 0. So they arise in many situations. So we say that Xn is zero distributed if and only if is singular value symbol is 0, and using the singular value the composition, we can prove this other characterization, which is asymptotically of low rank. So Xn can be written as a matrix of asymptotically low rank plus a matrix of asymptotically low norm. Interesting enough, if you consider F in L1, instead of consider the Teplitz sequence, you consider the Henkel sequence, that is the flipping of this Teplitz, which is displayed, then a result again by Fasino-Thiele tells you that this matrix sequence is distributed in the singular value sense as 0. So this Henkel matrix sequences are another example of zero distributed matrix sequence. So now we have three different classes of sequences: Teplitz, diagonal sampling matrices, and zero distributed matrix sequence. The GLT algebra is nothing else than the algebra of matched sequences generated by these three classes of sequences. And I try to describe in this slide. So you fix S and D, okay? In this, there is something where to put attention. Instead of talking about a GLT algebra, we should use the plural. So for any S and for any D fixed, there is a specific algebra. So you consider D-level tablets with blocks of size S, diagonal sampling matrices which are D-level and with blocks of size S, and zero distributed matching sequences of the right dimension. Then the algebra of match sequences containing DNA with A Riemann integrable, TNF with F Lebesgue integrable, and XN zero distributed match sequences is the GLT algebra related to SD. Notice that the definition, the original definition was much more complicated, but then it ended up that it can be described by these axioms, which are reported after GLT1, GLT2, GLT3, and so on and so forth. So the construction is completely equivalent to this set of axioms. Let's see what this axiom say. So GLT1, if AN is GLT with the symbol K, then always you have that A of n is distributed in the singular value sense as K. That is, if you plot the singular values, then they reconstruct the surface of the function K. Moreover, if all the matches are Hermitian, then you can obtain the eigenvalue distribution. But GLT2 tells you that this condition on the Hermitian character can be relaxed. So if AN is GLTK and AN can be written like XN plus YN, where Xn and Yn are bounded and every Xn is Hermitian, and you have a condition on the SHAT1 norm of Yn. So this non-Hermitian part is not that big in the sense that is SHAT norm divided by the size tends to 0 as n tends to infinity, then AN is again distributed in the eigenvalue sense as K. This GLT2 is important when treating, for instance, a second order operator plus a first order operator in order to get rid in terms of eigenvalue distribution of that part. Then GLT3 is what I was telling at the beginning. All the templates are GLT with respect to x, kx theta, where k does not depend on x. In fact, the templates, pure templates, represent usually the approximation of constant coefficient operators. So there is no variation with respect to the physical domain. And this is true for any f, which is L1 in I to the power d and s. Then the Na are distributed, are GLT with symbol kxd, which is ax. In that case, there is no Fourier space, and the A are Riemann integrable in 0, 1 to the power d, having values in ms. Zn, the zero distributed sequences are those having the symbol, the GLT symbol equal to 0. So these are the building blocks. Then you have the operation. If AN is GLT with respect to K, you take the sequence of the conjugate transpose, and this is GLT with respect to the conjugate transpose of the symbol. Then you can make algebraic operation. So you can make the things that we say to the students not to think. So if you take two matches and you make a linear combination, it is absolutely not true that the eigenvalues of the linear combination are the linear combination of the eigenvalues of the matches. But in this strange algebra, asymptotically, this is true. So you take AN, which is a linear combination with coefficient alpha 1, alpha 2 of the two GLT matched sequences, and ANI is GLT with respect to KI, then the resulting magic sequence AN is GRT with respect to the linear combination of the symbol. So if you go back to the item 1, you know that AN will have singular values which are distributed like the linear combination of the K, which is absolutely non-trivial if you think about it. If you take a multiplication, then you go and you consider that ANI is GRT with respect to KI, then also the product will be GRT with respect to the product of the functions. This is even less trivial. If you take two Table's matrices generated by L1 function and you make multiplication, the product of the two L1 function may fail to belong to L1, but still the distribution holds. And you understand why at the beginning, when giving the definition, the natural setting was that of the measurable function, because starting already from tablets, if you make the product, you can go out very easily from the L1 setting and go just in the world of measurable symbols. And if AN and the 6 is also very important, GRT with respect to K, and K is non-zero almost everywhere, which means that the minimal singular value of K does not vanish in a set of positive measures, then the sequence of pseudo-inverse AN is also GRT with respect to K to -1. This is not only theoretically important, but is probably the most important part with respect to practical application. Because when you have the solution of a larger linear system and you use a preconditioner, you have to invert the matrix sequence of the preconditioned matrix. If you stay in the GLT class, then you know that the symbol has to be inverted. And then there is a GLT7, which is related to the Hermitian setting. So Hermitian, and you consider F of AN, then the GLT is F of K. So this is very important for positive definite matrices when you make operation like the square root. This is important, for instance, in the geometric means. You can use these tools. And GLT8, I will not insist on this, but is also an interesting tool. So we have a machinery which has a lot of theoretical properties. Now we go to an example. Otherwise, we start to think that is too abstract everything. So I take an example in one dimension, but believe me, we did a lot of work on PDEs in several dimensions, also coupled, and technology works exactly. You make a discretization, in this case with equispaced grid, and you end up with this tridiagonal, which, since the dj are the sum of the element outside the diagonal with sign changed, the dj, this matrix coincides with the standard Laplacian 2 minus 1 minus 1 when the function a is identically 0. Interestingly enough, you can write this DNA very simply as the product of a diagonal times the tablets generated by 2 minus 2 cosine of theta plus some xn whose spectral norm tends to 0 as n tends to infinity. Then the use of the GLT items, and in particular the use of GLT3. So you go back to GLT3. So you know that the tablets is generated by the function, and the diagonal is also as a symbol, the function A. Then you use GLT5 in particular for the product and for the sum, and you end up that the symbol psi is A of x times 2 minus 2 cosine of theta plus 0, because 0 is the symbol of xn. So you can cook very automatically this symbol, and also in more variable, this is very easy. And you know in this way that ln of A has eigenvalues described by a bivariate function, A of x times 2 minus 2 cosine of theta. Strangely enough, even if it is a one-dimensional problem, you will have two variables. One variable for the physical domain where your A of x lives, and one variable for the Fourier domain. If you are in D dimension, then your sample symbol psi will have two D variables. D variable in the physical domain and D variable in the Fourier domain. And the X will belong to your omega with the only restriction, where the PDE is defined, with the only restriction that your omega is Peano-Jordan measurable, that is its characteristic function is a Riemann integral. And here it is interesting to make the plot. So we consider A of x equal to 2 plus cosine of 3 of x. We took size n equal 400, and we plotted the spectrum of ln and the uniform sampling of ax times 2 minus 2 cosine of theta. Here, of course, we arranged in non-increasing order. So the mathematical theory which is behind to the function we are seeing is a rearrangement of the function a of x times 2 minus 2 cosine of theta. And the other interesting fact is that already for n equal 400, the agreement is very good, which is non-trivial, because there was an excellent researcher, important person, Jean Golub, from numerical linear algebra. He was used to say, I'm not interested in asymptotical result, because in the long run, we will be all dead. And he was completely right. The luck with the asymptotical nature of the GLT is that usually the behavior is seen for moderate dimension, and this allows a practical application of the result. Then it is interesting that the error can be also analyzed, the error, the difference between the real spectrum and the sampling of the symbol. And if A is very smooth, it goes like n2 minus 1. But this can be improved a lot in several cases, and there is a lot of work by Bogoia, Becher, and Gruski, and also by my crowd, Italian and Swedish crowd, using extrapolation. So, for instance, if you have just the tablets generated by a monotonic function, you can discover that the eigenvalues are equal to the symbol on an equispaced grid plus h, which is n minus 1, times another function on the same equispaced grid plus h to the power 2 times another function in the same grid, and so on and so forth until the regularity allows. This asymptotic expansion is very important, because then you can compute the eigenvalues of a very large matrix by computing the eigenvalues of small matrices and then making extrapolation. This is, from a practical point of view, very, very remarkable. And as I said to you, of this I'm very enthusiastic, even if I'm more interested in theoretical results. But this is very, very striking, because you can compute the eigenvalues of a very large matrix without even touching the matrix, but working only with matrices of a much lower dimension than making extrapolation. So now I give a brief account on these blocking operators and GLT analysis, which is a kind of new result. So you consider AN, your matrix, and you consider this operator. So a block diag of dimension N1 and N. It means that you take only the block diagonal part of the right size. So AN of J will have dimension N of J. Then the interesting theorem is the following. If AN is GLT with respect to K, then this block diagonal structure retains the same symbol. So it is still GLT, which is non-trivial, and the symbol is the same. So if you consider Pn equal to this block diagonal, then it is interesting to observe that the difference is GLT like 0. So you can use the Pn as preconditioner and having the distribution as 1. And this is very much related to sophisticated methods used in domain decomposition, like additive Schwarz or multiplicative Schwarz. So again, practical consequences. But the other consequences are of the theoretical nature. So if you consider just a block diagonal operator with nu equal to, so only two blocks. So if you go back, the nu is equal to 2. So the block diagonal is made by the two blocks of the half size. Then, if you consider An minus Pn, you are considering Tn minus this block diagonal made of Teplitz matrices of size Tm, and what remains is exactly the Hankel structure which were considered by Fassino-Tilly. Then, because of the theorem of the corollary, which is written here, we know that An minus Pn is GLT0. So it is asymptotically low rank and asymptotically zero distributed. So you can recover the Fassino-Tilly theorem as a corollary of the corollary, let's say. But this is even more general because the Fassino-Tilly applies only to Teplitz. By considering general nu and general Ni1, nu, you can define differences as a class of generalized Hankel matrix sequences. And these generalized Hankel matrix sequences are all GLT with symbol 0 because they are zero distributed. By considering a general nu and general Ni1, Ni nu, and An, which is not Teplitz in this case, but is a general GLT, then again An minus Pn is zero distributed. And this defines a class of generalized locally Hankel matrices which are zero distributed. So any GLT matrix sequence is zero distributed, and hence it is GLT with zero symbol. And this can be used in practice in techniques which are called the flipping strategies. And there was recently a very good talk by this Chinese girl, which used in a clever way this technique. And the latter allows also to treat matrix sequences for system of partial differential equation. And this is very important with local scheme, both for distributional spectral analysis, if you want to know how the singular values and the eigenvalues behave, and for preconditioning. And this is also important because it can be used with very trendy methods in numeric analysis of domain decomposition. So also in this case, we have we arrive using this GL hack to having an answer for the asymptotic behavior of the singular values in the block case, which was the one considered at the beginning. The only negative thing, if you like, is that the symbol is really a complicated object. So you arrive to describe the capital F, which describes asymptotically the singular value of An, but the result is really non-trivial. You could have not guessed without using all this machinery. And this is just an example for convincing you that the eigenvalues of this block structure and the what is predicted by these functions are exactly of the same type. Then we are almost done. For you is late afternoon. Probably you are also a little bit tired. And so there is not very much that I want to tell more, except from the fact that there is a lot of beyond. So recently I've written a paper with 8 sections of open problems conjecture, because there are a lot of possibility. There are quaternions, there are type structure where the generating function are tensor valued. There is a stochastic type structure, a stochastic GRT, if you have a PDE where there is a stochastic term. There is a relation with machine learning. So there are a lot of results that can be still considered. So somehow the field is still full of research to be done. So with this, I conclude. Is 11 minutes before 5. Tatiana told me to go till 50, and I obey to her prescription. Thank you very much.
Thank you very much, Stefano, for the very good talk. Very interesting. So if there are questions, please. Stefano, I guess that this technique is applicable to systems which arise in inverse problems theory. So probably you could say a couple of words about that.
So if you are considering, for instance, the blaring and the noising problem, the model at the end is an integral operator. So usually this analysis applied to these metric sequences will tell you that the metric sequence is zero distributed. And in fact, the people working here talk about discrete ill-posedness of the problem, because the singular values of the matching sequence cluster to 0, and this can be predicted by this theory. But not only it can be predicted that is clustered to 0, but also that you have information on the singular vector related to the operator. So you know that the singular vector related to small singular values are those in high frequency, and this is an explanation of why the blurring and the noising problem is so complicated, because the noise lives in high frequency. So if you make the inversion, you risk to make the noise explode. So somehow it can be used also in this context. You are right, also with the variable coefficient point spread function, which is the model that describes the blurring in also in the variable coefficient case.
Mm-hmm. Thank you. More questions, please.
So I have to thank them because they resisted till now.
I have another, general question. For example, in the theory of differential equations, they apply a lot so-called transformation operators, which relate operators, differential operators, with variable coefficients to those without variable coefficients. So, and here, how well they are studied, because in the case of differential equations, for example, Schrödinger equation, one-dimensional, these type of transformation operators, they are just Volterra integral operators of the second kind. And what happens here with those matrices which would play the role of these transformation operators?
I have to be sincere in this. I have the idea of what is going on, so it could be explained again by using this theory. But it is also true that all the part which relates this GLT stuff with operator theory is just started. There are no, is a completely open field. So no one has worked, because, my point of view started from numerical analysis. It's difficult to convince a person from mathematical physics or from analysis to go in this direction. But there is a lot of things that can be combined. So somehow your question is for me very interesting because it's something in which a part of my group now is moving, how to connect what is known already in mathematical physics and in analysis with these techniques, but it's not done yet.
Okay, thank you.
Thank you to you.
More questions, comments, please. I think this is not the case.
So
then
we go to dinner.
There is a hand.
Helmut, please,
Yeah.
would you like to? Helmut, your microphone is switched off. So I see the hand, but Helmut, we cannot hear you, unfortunately.
So it seemed like the connection was not perfect.
Yes.
It's here. Yeah.
Now, yes.
So now it's working. Yes. My question is concerned with this papers about quaternion tuplet structures.
Quaternion.
Quaternion, yeah. I, in the past, were looking sometimes and interested. I did not see nothing. These are papers from 25, yeah? It's one paper with you from 25.
No, I have to be sincere. It's a paper in progress, in the sense that we have almost completed, but still is not in archive. And we give the equivalent of the Tertishnikov result in the case of Taperet's matrices generated by a function f in the variable L1 and quaternion valued, and is complicated. It's not trivial. It's not trivial. So quaternion are really fun. Then, if you want to describe all the eigenvalues asymptotically, it has been a lot of work. It is done. We have the result, but is not even submitted. It is ready more or less, but we have to still do some work for presenting in a better way. Otherwise, if papers are written in a too complicated way, no one will read, so it is no point to publish.
No, it's okay. I will just at the end of November go to Italy and to work.
Okay, so we meet. I will give you the paper.
Okay.
No. It's close to an end, but still we are polishing it.
Yeah, very nice, very nice.
Thank you.
Can tell about it. Maybe I can find interest for your work there.
Thank you very much. It's a pleasure.
Thank you.
But the eigenvalues you consider, they are always complex, not quaternions.
Yes, they are embedded in complex. Yes.